Everybody, welcome back to CSC 373, 548, the analysis of algorithms. I'd like to start off by asking if there's any questions about logistical matters. Okay, does anyone have any questions about things like notes or stuff like that? Yes, question.
Well, the graduate students are not really supposed to do the homework, the daily homework programs, correct?
Right. The graduate, there was some confusion on the homework assignments concerning what do you do with the daily homework problems, okay? Every day, I'm collecting the daily homework problems in the back of the room before class, okay? Undergraduates get credit for turning them in the daily problems, okay? It's like 5% of your grade. The graduate students, historically, I find, rebel at the idea of making them turn in daily homework problems. So I don't force the graduate students to turn it in. You know, if you want to turn it in, that's probably good for you. It's probably good for you to do it. If you want to turn it in, that's perfectly fine. I've listed the daily problems on both that sheet at the beginning that I gave out the first day of classes, which listed all the daily problems for the semester, and I'm also going to list them on the homework assignments that get passed out. So the fact that they appear on the homework assignments, you're not supposed to turn in copies of the daily problems, okay, when you turn in your big homework assignments. Okay, that's just there to remind you that you're supposed to be doing it. Okay? Yes. Okay, any questions, first of all, about the daily problems and how that works? Okay, question. Okay, what am I going to do about the lecture notes? Okay, starting now, the lecture notes for the first 3 lectures, sort of neatly typeset and all that, are sitting on the web page. Okay? So if you go back to the worldwide web page that we have, there's postscript copies of each of the first 3 sets of notes. I also went over to the basics print shop and deposited them all of my last year's notes. Okay? So you can go there and starting presumably sometime, my guess is tomorrow, you could buy copies of all of last year's notes, which are in content fairly similar to what I'm doing this time, although I'm changing them around a certain amount. But if you want to have something to copy from in advance of class, so you can just sort of jot notes in the corner, you might want to go and invest in the notes down at basics. Okay? But if you want this semester's notes, they're on the web page. Okay? If you want last semester's notes, the full year's worth, okay, rather than getting them online, those are available at basics. Okay? And if you want to go somehow to Xerox copies of the you would like to be able to buy Xerox copies or somehow make Xerox copies of the lecture notes without going to the web page, if an undergraduate or graduate student is willing to coordinate that with me, that we can sort of figure out. It turns out it's kind of a pain to update these things every time, but if there's somebody who would like to take charge of that, they could provide a class of service. Any other questions about that? Yes?
I had a look at your lecture notes on the home page. However, when I viewed them, there was like a small error message at the beginning saying something about some sort of parsing error at the beginning. I was able to view the notes properly, but there was like an error message.
Okay, if you have any electronic problems, send me mail, and we'll see what we can do about that. Ideally, I'll eventually be able to convert all the notes to HTML, but there's a converter that still isn't working right. But I think they're readable now. If you have any problems, just send me mail, and we'll take care of it. Okay, any other questions about things? Yes?
Yeah, I can't find the part numbers.
Okay, there's a question which some people have is presumably a lot of people seem to have started working on the homework, which is good, and some people are starting to find a need to have partners. Okay, and how many people do not have a partner and would like a partner? Raise your hand if you do. Okay, raise your hand high if you do. Okay, and now look around the room at people who have your hands raised, and see if you want to, no, seriously, this is not being recorded. Everybody's hand looks the same. I'll raise my hand too if you want. Okay? Look around the room and see if you can match up with somebody. Okay? Turn your head or do what you have to do. Because if for some reason you don't want to do that or you don't want to get matched up that way, send me your name by email and I'll send names back. Okay? But everybody who wants a partner should have one. You don't have to have a partner to do the homeworks, but I think it's a good idea. Okay? Any other questions? If you don't have a partner and you're afraid to raise your hand, if you want to come by after class and talk to me, I'll make introductions in person. Okay? Thanks a lot. Any other questions, logistical or anything like that? Okay, any technical questions from last time about the big O notation or anything about asymptotics? Okay. that said, let's start the real material for the lecture by first reviewing the problem of the day from last time. What was the problem of the day? The problem of the day asked, okay, there were two problems of the day actually. The first asked that show that for any constants a and b, where b is greater than 0, okay, show that n plus a raised to the bth power is in big theta of n to the bth power. Okay? And the secret to this, of course, is you have to show, if it's in theta, you have to show both the big O and the big omega. Okay? And to show these kinds of things, the straightforward way to do it, and the best way to do it until you really build up some intuition about this, is simply go back to the definition and prove what the definition says. So how do we prove the big O? Well, for the big O to be true, we must show that n plus a raised to the b is less than or equal to some constant times n to the b for all big enough n. Okay? So you have to sort of show what is a big enough n and what is a value of C1 to do the job. Okay? Well, the important thing, one way to look at it, there's lots of different ways you could do it. Okay? The way that I found easiest was to say, well, let's say that this constant was 2. Is n plus a to the b always less than or equal to 2 times n to the b? Okay? Well, it is if we note that n plus a is always less than or equal to 2 times n. Okay? Okay? And if we raise both sides, and okay, we take a look at that once we get n bigger than a, n plus a is always going to be less than 2n. Okay? And if we then raise everything to both sides, that's going to show that it's true. So that shows the big O factor. To show the big omega, what you need to show is that n plus a raised to the b is in fact greater than some constant times n to the b, once we get large enough. We set that constant equal to 1/2, we can do the same kind of trick the other way. Okay? Because we know that n plus a is going to be greater than n over 2 once we get n greater than a. Okay? And that shows it that you have an upper bound constant and a lower bound constant. Okay? And that should do it. Any questions about that? Okay? Very good. The second problem of the day, okay, is a little bit is a similar kind of thing. How can we show, is it true that 2 raised to the n plus 1 is that big O of 2 to the n? If it is, okay, then we can go to the definition. Okay, what is the definition? We really want to know, is it true, if this is big O of that, that means that 2 to the n plus 1 is less than or equal to some constant times 2 to the n. Okay? Well, what constant would work? Well, 2 would work. So long as your constant is 2, 2 times 2 to the n is 2 to the n plus 1. Okay? So long as your constant is greater than or equal to 2, this side is bigger than that side. Okay? And that works. Okay? For the second part, we want to know, is 2 raised to the 2nth power big O of 2 to the n? Well, it is if 2 to the 2 to the n, 2 to the 2n, is less than or equal to some constant times 2 to the n. Okay, that should be a 2 to the n. Now, 2 to the 2n is 2 to the n times 2 to the n. That you should remember from way back when. Okay? And so the problem really comes down to, is 2 to the n times 2 to the n less than or equal to some constant times 2 to the n? Well, you can cancel 2 to the n, and the question really reduces itself to, is 2 to the n less than or equal to some constant c? Okay? And no matter how big you make that constant c, you're eventually doomed to coming up with an n such that 2 to the n is bigger than that. So here we get a contradiction. This is certainly not true. Okay? So the important thing here is to see that we run into trouble. We can change the, we run into trouble because the exponent is not the same in both sides. Okay? Any questions? I guess because there's an asymptotic difference in the exponent here is really the difference, or a non-constant difference. Any questions about this? Okay, fair enough. What I'd like to talk about for the lecture today, again, we're starting out, we're in the process of a couple of lectures. This will be the last lecture on the preliminaries for the analysis of algorithms. Somehow the mathematics that you need to somehow give us a language to talk about analyzing algorithms. And we talked about the big O notation. The other tool, mathematical tool, that we're going to use a lot of, okay, are recurrence relations. Okay, and the reason for this is a couple of reasons for this. The biggest one is that when you're analyzing algorithms, particularly algorithms that are so-called divide and conquer algorithms, their time complexities turn out to be very naturally modeled by recurrence relations. Okay? And so one of our paradigms for analyzing algorithms will be you design the algorithm, okay, you see that it's got a sort of recursive structure to it. You then analyze its time by coming up with a recurrence relation based essentially on the structure of the algorithm. And then analyzing the algorithm reduces to solving the recurrence relation. So that's why we're going to be interested in recurrence relations here. Okay? And recurrence relations, which I think most people should have already been exposed to, are simply equations that are defined in terms of themselves. Okay? And there are two reasons why in life in general recurrence relations are good things. Okay? The first is that a great many functions are naturally expressed as recurrence relations. Okay? So for example, let's consider the recurrence relation a to the n, a sub n, equal to a sub n minus 1 plus 1, with an initial condition of a of 1. A sub 1 is going to be equal to 1. Well, what does that mean? A sub 2 is going to be a sub 1 plus 1, meaning a sub 2 is going to be 2. A sub 3 is going to be a sub 2 plus 1, which means a sub 3 is going to be 3. And in general, it should be clear that this recurrence really computes the function that can be solved in some sense. The function a sub n is really equal to n. This is just defines a linear function. Okay? And with similar kinds of recurrence relations, it turns out you can express any polynomial, okay, by a nice simple recurrence relation. Okay? You could also express any exponential by a nice simple recurrence relation. So for example, let's consider the recurrence relation a sub n, okay, equals 2a sub n minus 1, 2 sub n minus 1, where the initial condition of a1 is equal to 1. What does that mean? A sub 2 is going to be 2 times 1, or 2. A sub 3 is going to be 2 times 2, or 4. A sub 4 is going to be 2 times 4, or 8. It should be clear that this is now going to generate the function a sub n equals 2 to the n minus 1. So this is an example by having a multiplicative term in front of the recurrence, the recursive term. We can generate any exponential function using recurrence relations, using nice simple recurrence relations. And what's more, we can generate several weird functions which don't sort of come up naturally. Okay? For example, considering the recurrence relation a sub n equals n times a to the n minus 1. Okay? Or a sub n minus 1. Again, a1 equals 1. That means a2 is going to be 2 times 1, which means a2 is going to be 2. a3 is going to be 3 times a sub 2, which was 2, which means its product 6. The next term is going to be 4 times 6, 24, 120, 720. Okay? The point is that this is going to be generating the factorial function. Again, a very, very simple recurrence relation. But the interesting thing is factorials are functions that are, in some sense, hard to describe in any other way. They're not polynomials. They're not exponentials. They're just sort of weird functions. Okay? They're weird. That's why we give it a special symbol. Okay? Come up a lot. But the interesting thing is there's lots of functions that are hard to describe in other ways that turn out to be easy to describe with recurrence relations. Okay? So the first reason why we like these things is because they're, because they describe a lot of functions. The second reason is that it is often very, very easy to find a recurrence relation to count something. Okay? In this class, we're mostly going to be interested in counting running times. And by counting running times, what we're talking about is counting the number, counting the number of steps, the time complexity of something. Okay? But in general, for any kind of counting problem, it's very, very easy usually to come up with a recurrence relation, okay, that describes exactly what we want. And then our analytic problem simply reduces to solving the recurrence relation, which is somewhat of an art, but this procedure, but since it's so easy to sort of come up with the recurrence, this is often the right way to go. Any questions about why recurrence relations are good things? Okay? Very good. Now, the other thing to realize about recurrence relations, okay, which when I was in high school, I remember learning about mathematical induction. And mathematical induction was always this kind of amazing thing. Okay? You were supposed to, when you wanted to prove something, the claim was that you could prove it for the special case of n equals 1. You would somehow magically assume that it was true for everything else, and then prove one other case. And suddenly the teacher then said that was a proof. Okay? And I was always kind of amazed by this. Okay? Then when I got to learn programming, okay, the professor showed me a recursive program. They said, look, here you have this program. You say if you're not, n is not equal to 1, do this and this. Okay? If n equals 1, output this. Okay? And this is a program that computes everything, seemingly by magic, all those intermediate numbers. Okay? Now, why did both of these seem like magic? Well, because they're both doing exactly the same thing. Okay? An important thing to realize is that recursion is really the same thing as mathematical induction. In both cases, you have a general case and a basis case. Okay? And that the way that we're going to solve a general problem is by sort of starting with the general case, using the general case to break it into smaller cases, and keep breaking it into smaller and smaller cases until we get to our basis case. The general case enables us to combine things properly. Okay? So once you realize that these two are the same, that's a big insight. Okay? And it turns out that we can use the tool of induction to help us solve recurrence relations, which are essentially recursion. Okay? What was the idea of induction? Well, induction provides, in general, a very easy way to prove something is true. Okay? Once you know that what you're actually trying to prove. Okay? So when you want to solve a recurrence relation, one of the easiest ways to do it, okay, is to, in some sense, look at small values, try to guess what the solution is, and then prove that by induction. Okay? So for example, suppose I've given you the following recurrence relation. The n, t sub n is equal to 2 times t sub n minus 1 plus 1 with an initial condition of t of 0 equals 0. So how would you solve such a thing? Well, the way that I would probably proceed to solve it, I'd start making some small values. I'd plug it in. Okay? T of 0 is 0. T of 1 is 0 plus 1. T of 2 is 2 times 1 plus 1, it's 3. T sub 3 is going to be 2 times the previous one, which would be 6 plus 1, which is 7. When you go through a couple of these things, hopefully you'll start to notice a pattern. Okay? What is the answer to this recurrence relation? Okay? By looking at this pattern, how many people by looking at this pattern could pretty much guess what the solution is? Okay? How many people couldn't guess what the solution is? Okay? You got a majority of people, well, okay, a majority of the people who answered could guess. Okay? Okay? The majority of people who didn't answer presumably couldn't guess. Okay? But the basic idea would be to take a look at this thing. If by playing around with these numbers, you'll start to see that they look like they're doubling each time. Okay? And to me, that would start to say, hey, this has to be something like 2 to the n. Okay? And then by fooling around with it, okay, it seems to me that it's reasonable, that I would probably eventually figure out that you mean 2 to the n minus 1. But once you have the answer to this recurrence, or what the proposed answer is, we can prove that by induction fairly easily. What was the 3 steps of induction? The 3 steps of induction was first showing that the basis was true. What was the basis case? Well, the basis case, let's just try t of 0. If this is true, 2 to the 0 minus 1 is going to be equal to 0. Is it? Well, 2 to the 0 is going to be 1, because anything to the 0 is 1. 1 minus 1 is 0. Sure enough, the basis case is true. We've proven the basis case. Then comes the magic. We assume that for all numbers in between, okay, this formula holds, meaning t to the t sub n minus 1 is going to be 2 to the n minus 1 minus 1. Now we use that assumption by plugging it back into our formula. Okay? So what is 2 to the 2 times t to the n minus 1 plus 1? Well, we know that t of n minus 1 is 2 to the n minus 1 minus 1. Multiplying that out, that becomes 2 to the n. 2 times minus 1 is minus 2. Minus 2 plus 1 is minus 1. Lo and behold, we get an answer of 2 to the n minus 1, which is what we wanted. Okay? And so this has to be true. We've just proven it by induction. Okay? So remember this close relationship between induction and recursion. Okay? To show that, because this turns out to be a good way to sort of work with these things and to really understand you know what's going on. Okay, any questions about the proof by induction? Or proofs by induction in general? Okay? Very good. Now, when it comes to solving recurrence relations, we're not going to, I mean, sometimes when people teach a course in analysis of algorithms, they'll spend several classes on really learning how to solve recurrence relations. Here in this class, I'm going to be more interested in design of algorithms. Okay? So I'm going to try to give you what I consider as much of a cookbook procedure to solve recurrence relations as I can. Okay? If you're interested, I encourage you to read more. The text in the book is very good. Okay? But I'm going to give you a sort of 4-step approach that I use when I'm confronted with a recurrence relation. Okay? Solving recurrence relations is somewhat of an art. There is no one canned procedure that is guaranteed to always work. Okay? But I will tell you what I would do if I was in a dark alley confronted with a recurrence relation. Okay? There's 4 things to do. The first thing is to realize that there's certain cases of recurrence relations that can be solved mechanically, that require no thinking. You can look at them and say, woof, it can be solved. Okay? And the case that is most famous and comes up most often are what we call linear, finite history, constant coefficient recurrence relations. Okay? If you took a course in differential equations, you probably learned this when you studied difference equations. If you took a course in combinatorics, you almost certainly went through how to solve this. Okay? It's these kind of equations. What does this mean? Well, we say that the history of a recurrence relation is how many terms back it goes. Okay? So look here. A sub n depends on a sub n minus 1 and a sub n minus 2. It depends on 2 events in the past. The total amount of history it requires is 2 terms. 2 is a constant. So this recurrence relation is constant history. Okay? The coefficients are the things that are being multiplied by the recursive terms. We've got a coefficient of 2. We've got a coefficient of 2. Each one of those coefficients, okay, is 2. That's a constant. Okay, there's also a coefficient of this other degenerate term, which is 1. All of these are constants. Okay, it's got constant coefficients. It's got finite history. Okay, it's got nothing else in there really. Okay, this recurrence relation can be solved mechanically. Okay, you learned how to do it in a differential equations course. You learned how to do it in a combinatorics course. Okay, if you didn't, you can look it up in any one of these books if you have to see one. Okay, the basic procedure, just to remind you, if you've seen it, consisted of taking that recurrence equation and finding some kind of recurrence relation, finding a quote-unquote characteristic equation, which involved sort of doing something to these terms, like a squared would corresponded to 1, 2a corresponded to this, and 2 corresponded to that, okay? Or something like that. Okay, you extracted an equation. you then solved this equation to get roots, which were going to appear in the exponents of what you were doing. And then you took care of repeated roots and inhomogeneous parts, okay? And then found the constants to finish the job, okay? I don't remember that procedure, okay? I don't have to remember that procedure. I know that the procedure is there, and I know what kind of functions it will work for, okay? It will work for linear, finite history, constant coefficient recurrence relations. Whenever I see one of those, I know it's solved, okay? If I actually need to solve it, okay, I'll confess I cheat a little bit. A system like Mathematica or Maple has a program in it that will solve it for you, okay? So this is a special case, easily handled. It's done, as far as I'm concerned. Okay, if you need to solve it, that's how you do it. Any questions about linear, constant coefficient, finite history, recurrence relations? Okay? Learn to recognize them and pronounce them finished as soon as you recognize them. Okay? Or if you need them, actually solve them. But it shouldn't be a problem at this point. Any questions? Yes?
Is there Mathematica for Unix?
There is actually, if you're on the graduate machines, there is a there is Mathematica running on several of the on some of the machines. Okay, in my lab, I guess there's sort of but Maple runs on all the machines. The university has a site license for Maple, so there is no reason why anybody who needs to solve one of these things can't go and slither onto a Maple system someplace and just say solve. Okay. So it's easy to do once you recognize it. Any questions? Okay, so that I pronounced the trivial case. The second thing that I do, if I'm given a recurrence relation, if it's of that type, the problem is solved. Okay? If it's not of that type, what can I do? My second line of attack is to try to guess a solution, okay, and prove the solution by induction. Okay? And to do this, what I usually do is, again, how do you guess a solution? Part of it is a question of experience. You look at enough recurrence relations and you sort of know what's going on. We'll talk a little bit later about a structure called the recursion trees, which make things a little easier to guess. But the simplest way to guess is to actually sit down and play around with small values. Okay? One thing that a lot of students refuse to do is to sit down and experiment. Okay? They see when you sort of work out mathematics in a textbook, everything's neatly out. Usually students assume that when you want to solve a problem, it sort of comes from the head whole. And that's completely wrong. The way that I solve these things is I play around with the problem. I construct examples. Okay? I sit down and see what the value of the recurrence is for small values. Try to make a guess what it's doing for large values. Only by playing with it can you get some kind of an insight into it. Okay? So once you have the recurrence formula, you try to guess what the solution is. And once you have the solution, you use induction to. One thing that may not be obvious at first, okay, but turns out to be useful in this class, is in fact you can use induction or any other mathematical techniques you've learned on the big O notation, okay, and prove things using induction despite the fact that you've got big O's in terms. So I'd like to go through a proof of something like that. Suppose we would like to prove that t sub n are equal to, okay, suppose we have some function t sub n that is always less than or equal to 2 times some constant times n over 2 log n over 2. Okay, well, we've got floors functions here, plus n. Suppose we'd like to prove that this function is, okay, in big O of n log n. Okay? How would we prove something like that? Well, what we really mean is that what we want to prove is that this thing is less than or equal to some constant, okay, n to the log n for large enough values of that constant and n. Okay? How do we prove it's true by induction? Well, we assume it's true for all smaller cases. I mean, you have to prove the basis case, okay? The basis case you get by plugging things in, okay? And here you plug in the values of 2 and 3. That turns out to be small enough. That satisfies. But the heart of doing the, okay, is going to be proving the general case. So how do we prove that this value is less than 2 times c n over 2 to log of n plus n. Really what we want to do is to show that this is less than. Okay, well now we want to sort of work on this and massage it a little bit. The first thing to do is to notice that in this expression we have a floor function. What was the floor function? The floor function meant that we chopped off the remainder. Okay? So the floor of 3 over 2 was going to be, that's 1.5. We chop off the remainder, that's 1. Okay? So the floor is always less than or equal to, okay, the number itself. Okay? If the number was an integer, if it was the floor of 5 is 5. The floor of 0.999 is 4. So what we do is take a look and see that 2 times the floor function here. If there was a parentheses, 2 times n over 2 would be exactly n. Okay? Instead what we have is a floor. What's important to see is that this thing is actually less than n. Okay? So we can replace it by n, and the term is always going to be bigger, or no smaller than it was before. How many people believe that? How many people don't believe that? Okay? So everybody believes. Okay? So by dropping the floors, we've made the thing larger, but that's okay because we're worried about sort of big O kinds of things, and we see the direction of the thing has sort of worked properly. Now we want to work on what is the log of n over 2. Okay? Well, by using your formula, the log of a over b is the log of a minus the log of b. The log of base 2 of 2 is 1. Okay? So now we're reduced to saying that this thing is less than or equal to some constant times n log n minus some constant times n, that's the Cn times 1, plus n, that term here. Okay? Now what do we know? We've got C times n log n minus C times n plus n. Whenever that constant, okay, is bigger than 1, this term is going to go away. Okay? So long as that constant is greater than 1, we know that this term is going to get swallowed up, okay, and that this quantity, okay, and that this quantity is, okay, whenever this constant is less than, I think the direction here is wrong. Whenever this constant is less than 1, this term is going to be bigger, okay, and this side's going to be bigger than that, proving what we had wanted, okay. So any questions about that? Okay, actually I may have gotten a little garbled here at the bottom, okay.
It's greater than C, then Cn is more than n.
Right.
So you can just discard both of them.
Right, okay, that's actually, so this sign is right is what you're saying. Yeah, the sign is right, actually, okay, I was bluffing, okay. What's the point here, okay? Whenever this constant is bigger, this term is going to go away, okay? This thing is going to be equal to that. If we put this thing away, this side is only going to be bigger than that, okay? Because this quantity, we're replacing this thing by something that's bigger than it, okay? And that, you know, so this side has to be bigger than that whenever that constant is big enough, okay? And to show what the value of n naught that you needed to start with, we simply went to the recurrence relation and plugged in small values until we got a value that was larger than our such that the basis case would satisfy it, okay? And it turned out either 2 or 3 would work. Okay? So once we set our constant, we could go, our value C, we could go back to set our n naught to show that this happens to be true. And that would prove it sort of in the big O notation. Any questions about that? I'm sorry if it was a little confusing. Okay? Again, we're not usually going to be doing too many analyses this carefully. Okay? But the moral is that by going back, you can actually use induction, tools like induction, on things like you know, terms expressed in the big O notation. Just by going back to take the big O notation and rewrite it as less than or equal to some constant times that. And then figure out where the constants hold. Any questions about that or anything else? Okay. The third technique that I do when I am confronted with a recurrence relation, okay, is you can try something called back substitution. What is back substitution? You start from the original value, the big value, okay, and keep plugging the recurrence relation into itself until you go back and get what you think the answer is. In some sense, the way that you would prove something by induction, typically from induction well, not proving by induction, there's two ways when you look at a recurrence relation to try to guess what the answer is. One is you look at small values of n, sort of solve it explicitly, build up a table, n equals 1, n equals 2, n equals 3, n equals 4. The other thing that you could do is try to solve it for big values of n by plugging the equation back into itself, okay, and doing this repeatedly until you notice some kind of a pattern. So for example, suppose we want to solve the recurrence relation t sub n equals 3 t sub n over 4 plus n. Okay? Usually when we talk about big O and type of things, we can ignore the floors. So if it makes things easier for you, at least as a first guess to help you get insight into it, you can drop it and play around with it. But let's see if we can solve this recurrence relation. Okay? The way that I would solve it is by taking the recurrence relation and plugging itself in for it. So what do we know? T sub n is going to be equal to n plus 3 times t sub n over 4. What is t sub n over 4? T sub n over 4 is going to be, if we plug itself in, 3 times, okay, no, this could be 3 times t sub n over here. What is t sub n over 4? Well, t sub n over 4 is going to be the argument term, which is n over 4, plus 3 times the argument term over 4, which is n over 4 over 4, meaning n over 16. So what I've done is I've taken this thing, and I've taken this recurrence relation and plugged in the value of t of n over 4 into it. Okay? And that gives me this expression. Any questions about what I did there? How many people see what I did with the substitution? How many people don't see what I did with the substitution? A few people, okay? So what I'm doing here is as follows. What is t sub n over 4? Okay? Plug it into this formula. It's going to be 3 times, okay? I'm going to replace n by n over 4. That's going to be n over 16. Okay? Plus n. N is now n over 4. Okay? This is what I claim t sub n over 4 has to be.
Can you refocus?
Refocus, yes, probably. Okay. That's actually, my handwriting usually does better when you can't read it too clearly. How does that look?
No, I mean, no, just change the center so that you can see the whole equation we just wrote.
Oh, okay.
Yeah.
Sorry about that. Okay, okay. I'm not. There we go. Ah, okay. Very good. Okay. Well, maybe better. Okay. What's the point here? Okay. I want to know, in order to figure out what is t sub n equal to, I know by definition t sub n is equal to 3 times tn over 4 plus n. That's all that I have to go on. I'm trying to solve this thing. So what does t of n over 4 have to be? If I take this expression and plug in n over 4 in place of n, what do I get? My claim is I'm going to get 3 times, let's maybe write it a little neater, okay, 3 times n over 4, which is n over 16, plus the argument, which is 3n over 4. Okay? Is it clear to everybody that t sub n over 4 is equal to this? Okay? That's just plug and chug. Well, let's now stick it in where it belongs. Okay? If you want to know what t of n is, okay, in order to solve t of n, you need to know what t of n over 4 is. Well, I just told you. That's what t of n over 4 is. So let's take this expression and stick this thing in. And when we do that, we now have the following formula. Okay? And the hope would be that by looking at this formula, you can now guess a pattern. Can anybody take a look at this thing and guess what the answer is? Okay. No, I couldn't. Okay. So what do? I stick it in again. Okay. I've now got a term here which has a t of n minus n over 16. To solve this thing, I'm going to stick the t over n equals 16 value in and try to keep plugging it in until I notice a pattern. So what is going to happen? What is t of n over 16 going to be? Well, it's going to be 3 times t of n over 64 plus n over 16. Okay? And every time I insert these things, I've got various parentheses and things that have to be maintained. Okay? So the point is that by keeping to plug these things in and taking a look at the terms that I'm leaving, the hope is I can guess a pattern. And if you plug things in for 3 levels and do the algebra right, you'll start to get a look and noticing that you've got an expression like this. N plus 3n over 4 plus 9n over 16 plus 27n over 64. Looking at that, hopefully you start to see a pattern. At this point, I see a pattern. Okay? The things on here are powers of 3. 3, 9, 27. The things below are powers of 4. 4, 16, 64. The answer to this thing is going to be the results of summing up these 3 to the n over 4 terms. Okay? That's what you hopefully will learn by doing the back substituting. You keep sticking things in there until either you notice a pattern or you're tired of doing it. Okay? I usually give it at least 3 or 4 levels before I abandon hope. Okay? But in this case, it should now be obvious what the answer is going to be. The terms that are getting left are going to be the sum of, okay, 3, okay, to the I over 3/4 to the I times n. Okay? That's what all these terms are. Okay? And eventually, if I keep substituting this thing in, this term is eventually going to go down to being n equals t of 1. T of 1 is going to be a constant. So there's 2 components to this that I'm going to have to worry about. One is the additive stuff that's getting left behind. The other one of which is going to be the remaining basis case, which eventually we're going to get around to evaluating. Okay? When you substitute things in, basically what you end up getting are this term plus that. Okay? What is this term? Well, we can factor out the n from the sum, okay, because the sum is form of I. It's an infinite series. The sum as I goes from 0 to infinity of 3/4 to the I. This is a geometric series. Geometric series is converge. You learned that back in calculus. Okay? So in fact, we know that the sum of this thing, okay, is going to be some constant. If you want to know exactly what constant is, you look up that formula in the book. I can never remember it, even though it's fairly simple. Okay? But I do know what book it's in. Okay? Okay, and it's simple. It's something like, it's always something like, what is it? This constant minus 1 over, again, it's a simple formula. Okay? Okay? Most people probably remember it. Okay? But again, I don't like to remember things. I like to look things in books. Okay? But the point is, this is a constant. Okay? That much I do remember. So I solve it. That constant turns out to be 4. This turns out to be 4 times n is a solution, plus this term of how many times I'm calling the basis case. Okay? And this is maybe a little bit hard to see that it's going to be a term like this, okay, until you start using a technique called recurrence trees, okay, which is what I'll talk about in a second. Okay? But the basic point is that you've got 2 terms. This is going to be little o of n. So this is bigger than that. The sum of these 2 is going to be o of 4n or o of n. Okay? Any questions about that? That's the back substitution technique. And again, it's a good thing to try. And so long as you keep your algebra straight, okay, you're likely to notice what the pattern is. Okay? Any questions? Now, the easier way to see what's going on with back substitution, okay, what's really what I usually do, okay, is using a technique called a recursion tree. And what a recursion tree is a picture of doing back substitution. Okay? What is back substitution? We're starting at the root value of the recurrence at n. And we keep sticking itself in, okay, replacing it with itself. Okay? What we're going to have to do when we do these substitutions, there's two things that you have to keep track of. The first thing is the remaining argument, okay, that needs to be evaluated. Okay? The second thing is the stuff, the additive amount that you were adding, okay, that was being added each time you sort of substitute the equation in for itself. Okay? You've got to keep track of both of those things when you're solving the recurrence. And in fact, the value of this recurrence is the sum of both of those components. So how do we keep track of it? I say we draw a picture of it. We draw the picture of what happens when you try to evaluate T sub n. Okay? In this case, the recurrence relation, T sub n is equal to 2Tn over 2. In the course of finding Tn, what we do is we split it up so that we get T of n over 2 plus T of n over 2. That's the recursive call that's happening. What is the recursive call that happens with T of n over 2? We split it into two pieces. T of n over 4, T of n over 4. What happens with the T of n over 4? We split that into two pieces. T of n over 8, T of n over 8. This is a picture of what that recurrence relation is doing. Okay? It's a picture of sort of the chain of substitutions. What is it that we're going to ultimately have to count from this recurrence relation? Well, we need to count the sums of the basis cases. So we have to count how many leaves there are, ultimately. Okay? And getting a look at this picture will help tell us how many leaves there are. Okay? The other thing that we need to count is this n squared term. Every time we substitute this thing in, the price for doing this substitution is n squared, where n is the value of the argument. Okay? If we think about this as a recursive algorithm, if we were to solve a problem of size n, we reduce this to solving two problems of half that size, plus doing this n squared amount of work to actually patch this thing up. This is the price we pay for evaluating this recurrence. Okay, once. So let's keep track on another side, a tree that shows the price that we're paying. Okay? The recurrence relation was Tn, okay, 2 equals 2 Tn minus over 2 plus n squared. So the first time we pay is n squared. The second, after we now look at it, our argument is n over 2. We pay that amount squared. That's n over 2 squared, which is n squared over 4. On this side, we had an argument of n over 2. What was the price we paid? N over 2 squared, which was n squared over 4. Okay? Take a look below that. The argument here was n over 4. We paid that argument squared. Okay? Or n squared, or n over 4 squared, which is n over 16, n squared over 16. The important thing to see about this diagram is that this diagram captures all the stuff that we're adding in the recurrence. There is the leaf stuff. Okay, this is the structure of how we're breaking things down. And there is the additive stuff. Okay? And with the picture, it's not that hard to see the structure of what you're doing. But the other thing that you can do with the picture that's nice is the picture helps you add things up. What is the value of this thing? Well, what is n squared equal to? The sum of n squared, well, n squared is one term. That adds up to be n squared. Let's add up the rows of our tree. What is n over 2 squared? That we said was n squared over 4. What is n over 2 squared? That's n squared over 4. N squared over 4 plus n squared over 4 is n squared over 2. Write that down. What is this? You have n squared, n over 4 squared. That's n squared over 16. And you've got 4 of those terms. 4 times n squared over 16 is n squared over 4. if we take a look at this term and look at what's going on as we move down the tree, what is happening to the sums of the stuff that we move down the tree? Okay? What's the difference between here and here? What happened? It got cut in half. What happened when we moved down from here to here? It got cut in half again. Each time we move down the thing, on the ith level, what is the value of all the stuff that we're adding up on the ith level? Okay? It's n squared divided by 2 raised to the ith power. Because each time we're getting half as much as we had before. Okay? This means that we've got a geometric series. Okay? If you want to add up all of these things, what you're really adding up is that t sub n is going to be equal to the sum as I goes from 0 to infinity, if you want, of n squared over 2 to the I. Okay? You can factor out the n squared. This sum reduces to n squared times the sum as I goes from 0 to infinity of 1 over 2 to the I. Which, again, that you should be able to do by using that. You know, that's sum of a geometric series. This is one I don't even have to look at the formula for. This adds up to be 1 or 2, depending upon where you start it from. Okay? And so this is going to be a constant. The sum of this thing is, in fact, going to be equal to theta n squared. So by looking at the recursion tree and adding up the rows of the recursion tree, okay, summing up along those rows, we can accumulate what the stuff is that we're actually adding up. Okay? And by looking that way and plugging it in, okay, that gives us a way to look and see what our recurrence relation is doing. That's how I do back substitutions. I build these recursion trees. Okay? Any questions about that? Okay? Now, again, there's 2 components to any solution of the recurrence. There is the additive stuff, okay, that we're dropping, the residue work we're spending, and we're also adding up basis cases. Where do the basis cases get added up? That corresponded to the number of leaves in this tree. So how many leaves were there in this tree? We started out with n. We broke it up down into n over 2 and n over 2. I'm going to keep breaking that down, n over 2 into n over 4, n over 4. Every number value from 1 to n, eventually we're going to end up with breaking this down. When are we going to stop breaking it down? What's the value of n for which we're going to stop breaking it down any further? Okay, what is the value of n? We typically know the answer.
Well, log n would be kind of the end, because then you have all n elements divided over the tree.
Oh, okay, what you're saying is how high is this tree? Okay, you're saying the tree is of height log n. Okay? That's really equivalent to saying how many leaves are there in this tree. Well, the number of leaves is going to double each time we go through. So if the tree had height 1, there would be 2. If it had height 2, it would have 4 leaves. If the tree is going to have height log n, it's going to have n leaves. So in fact, the sum of this thing is going to be the residue that gets left behind plus n times the value of the lowest leaf, which is t of 1. So in fact, to this quantity, we would have to also add n times t sub 1. But what is the basis case of our recurrence? Presumably 1, 2, n times some constant. If all we're interested in is in the theta notation, that gets washed out. Okay? So although there's 2 parts to it, in this case, the value of the leaves is ignored. Okay? Whereas is unimportant relative to the stuff we left behind. That's not necessarily true, but it's true for this recurrence. And you got to go look at both components in order to do it. And the way to do that is to simply look at the recursion tree. Okay, any questions about that? About how you use recursion trees to do it? Okay? Again, this lecture is kind of on algebra, mathematical techniques, and people I think get leery about that. They don't see where the insight is. It's all plug and chug, plug and chug. Okay? Or suddenly people are pulling formulas out of the air. The idea behind solving a recurrence relation and understanding what a recurrence relation is going to do is to build this recursion tree. Draw the picture of what's getting left behind and see the structure of it. Almost always, if you add up the rows of what gets left behind, you'll see something interesting happening. Yeah? Okay, that's a good question. In fact, I would probably not explain that the tree has height log n. What I would probably first see, if I want to say, why do I understand that that tree has that height? The first question I would ask myself is how many leaves the tree has. The original question was sort of, the answer was given differently. It's the same answer. If I were looking at this question of saying, what is the height of this tree? My way of looking at that would be to say, how many leaves does this tree have? Okay? The important thing to see, the way that I would see that it has n leaves, okay, ultimately, is to see that in the course of, you're starting out with a number of n, and you're dividing it equally into two pieces. If I think about it, you've got n things here, and you're splitting the n things into a pile of 2n over 2 things. And you're splitting that pile in half, and you keep splitting that pile in half. When do you stop splitting the pile in half? The answer is when you can't split it in half, when there's only one thing. So my claim is it should be, when you look at this thing, it should be clear that this tree is going to have n leaves. That's the way that I think about it. First of all, this tree has to have n leaves. Okay? How many people believe the tree has n leaves, or see why that is? How many people, most people, how many people are still confused with that? Okay, a couple people. The way that I would look at it is, if you don't believe that, draw the picture, okay? Plug in numbers. Suppose n was equal to 4, okay? Let's come back here. If we want to find 4, how many leaves does a tree with 4 things have? Well, 4 over 2 is 2, and 4 over 2 is 2. 4 over 4 is 1, 4 over 4 is 1, 4 over 4 is 1, 4 over 4 is 1. Look, okay? You've got, starting out with an argument of 4, I've got 4 leaves. That should be enough to convince you that for n equals 4, you get 4 leaves. If you're not completely convinced, try it for the case where n is equal to 8. If you're not convinced then, try it for n equals 16. If you're not convinced, try it for n equals 32. Convinced fairly soon, you'll be convinced. Okay? So no, it's important to get this intuition. Okay? I find that it's very important for me to construct explicit examples in understanding these things. Okay? So this tree has n leaves in it. The original question is, why was the height of this tree log n? Okay? Well, let's think about that. Okay? We have n leaves total. Okay? How many nodes do we have on the second level? Okay? Given that we had 1 node on the first level. We have twice as many. How many nodes do we have on the third level relative to the second level? Twice as many. How many on the fourth level relative to the third level? Twice as many. How many nodes do we have after I levels? It's how many times do we multiply 2 till we get n. And that is exactly what log n is. Okay? That is the intuition. That's how you have to feel it. Okay? We want to know how many times can we double 1 until we get up to the n leaves that we know we have. Okay? And that's why the height has to be log n. Okay? That you got to feel in your bones. That's the definition of log n. Okay? And I find that's how I think about it. I don't go back to an equation. Okay? You got to sit back and think about it in terms of what the function is. Any questions about why the tree is log n, okay, in height or has n leaves? Okay? So the bottom line is, in trying to use recursion trees, I find you draw a picture of the trees, okay, what's actually happening, and then look at the pictures and analyze it from that. That's my technique, and that I find works very well. Okay? Any questions about that? Okay, so recursion trees and back substitution is step 3 of my 4-step approach. What is the 4th step? Okay? The 4th step is using a powerful theorem called the master theorem, okay, which is described in your textbook. What is the master theorem? The master theorem is a plug-and-chuck way of solving a large class of recurrence relations. Okay? So I think it's fair to say you should probably look to see if you can use the master theorem before you spend a lot of time back substituting or thinking about induction. What is the master theorem? The master theorem states as follows. You've got two constants, a and b, okay? You've got a function, f of n, and you've got a recurrence relation that looks something like this. T sub n is going to be equal to some constant times t of n over b plus f of n. So f of n is the additive stuff that got left behind. A is the coefficient we're multiplying t sub n by. And b is how much are we hacking that argument down each time we do that substitution. Not all recursion relations look like this. Okay? But a lot of the ones we're going to study for this class do look like that. If your recurrence relation is of this formula, okay, then there are three possible answers that you can get to this recurrence relation, depending upon what the value of a is, what the value of b is, and what that function f of n is. Okay? What are the possible cases? Suppose that additive function, f sub n, okay, is big O of n to the log base b of a minus epsilon. Okay? What does big O mean? It means that this is an upper bound for it. F sub n grows slower than this, or no faster than this. What is this thing? N to the b, base b log a. A and b were constants, so you can find out what that value is by sticking it in your calculator. Okay? If f sub n is less than n to that constant minus some other tiny constant, okay, then the answer to this recurrence is theta to the of n to that constant. That's what the answer has to be if that condition is true. Another possibility is that f sub n is in fact exactly theta of n to the log base b of a. Okay? If that function happens to be exactly that, the answer is going to be theta of n to that constant times log n. Okay? That's what the value of the recurrence is. If f sub n grows bigger than this bound, which is n to that constant plus some constant, if it grows faster than that, okay, and if some other technical stuff holds, then the value of this recurrence is theta of that function. So there's three possible values here. Okay? If f sub n is very, very small, okay, small being defined as this, we get this value. If f sub n is very, very big, meaning that f sub n is this, then we get this value. And if f sub n is just right, okay, we get this value. Okay? That's what the answer is. The master theorem is called the master theorem because it can solve any one recurrence of this type, modulo there's certain funny things it can't. But just about anything you'll see of this type, it can solve. And the problem reduces to finding out which one of these cases hold, and then say, yes, master, that's what the answer is. Okay? Any questions about what the theorem is? I'll show you an example in a minute. But any questions about the idea behind the theorem? Okay? Yes?
So the f is not supposed to have any t term in it.
No. The additive stuff, that's sort of an important point to see about the recurrence relation. Remember that there's sort of a history part of the recurrence, and then there's sort of the additive stuff. Okay? The important thing to see is that in this case we've got the history part of the recurrence is covered by the t's. Okay? This f sub n is the additive stuff that gets left behind. Okay? So you're right. It cannot. We're assuming that there's only, in some sense, one history term here.
Yeah.
Okay? If you have a higher history term, you're out of luck. Okay? But for the algorithms we'll analyze, it turns out that that's not a problem usually. Okay, but it's a good point. Master theorem does not solve everything, but it probably comes pretty close to solving most of what we'll do in this class. Okay? Any questions? So how do you apply the master theorem? The way you apply the master theorem is you simply compute these conditions, plug it in, and see what applies. Now it's just algebra. Okay? So let's take a look. Which case of the master theorem applies? Okay? The key value, let's zoom it up a little bit. The key thing in the master theorem is going to be this n to the base log b of a. That's really what the switch point is in the master theorem. So when you want to decide which case to apply, what I would do is you take the equation and you read off what is a and b. A is 4, b is 2, f sub n is the additive stuff, f sub n happens to be n. Okay? We've parsed our recurrence relation into these three parts. The key issue to decide which case applies is how does our value of n relate to the function n to the log base b of a? Well, what is the log base b of a? What is the value of 2 that you have to raise 2 to get 4? 2 to the 2 is 4, right? So, in fact, what we really want to know is n in big O of n to the 2 minus epsilon for some very, very small but non-zero value of epsilon. Okay? So what is something that is very, very small but bigger than 0? 0.000001. Okay? Is n in big O of n to the 1.999? Okay? Is it? How many people say yes? How many people say no? Okay? People who said yes were right. Okay, well, everybody who said anything said yes. Okay? So the real question is n in n to the 1.9999999? Yes, because that's n to the 1 is 1 less than 1.99999. The answer is yes. Case 1 of the master theorem applies. You look it up. In fact, okay, it turns out to be f of n, which is, if you look it up, it turns out to be this value here, theta of n to that. Just looking it up from the table. Okay? See, the answer here for case 1 is n to the that, which we said was 2. What if we consider the second case of the master theorem? Okay? Or we have a recurrence relation like this, where t sub n is 4 tn over 2 plus n squared. Again, what do? We read off what is a? A is 4. What is b? B is 2. What is f of n? N squared. We want to ask ourselves, is n squared in, well, this in big O of, well, this was 2 minus epsilon. Is n squared in big O of n to the 1.99999? No, 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 as someone pointed out. Okay? Why is that? This constant because of that little epsilon. It can be very, very close to 0, but it's got to be bigger than 0. Okay? So this side is going to be slightly bigger than that. Okay? So it's not true if epsilon is greater than 0, which is what we needed for case 1 to apply. But it's true if epsilon is equal to 0, which is exactly what case 2 is asking for. So in fact, case 2 applies, and the value of this recurrence relation is in fact theta of f sub n log, okay, f sub n. What is the log of n squared? Okay, 2 times n, okay? 2 times log n, okay? So this is going to be 2 times n squared log n. The 2 gets wiped away in the theta notation. We don't have to worry about it. Okay? So this is case 2 of the master theorem. Any questions about case 1 or case 2? Yes?
Can the master theorem be applied for multiple discrete cases by taking it as a summation of 2 other terms, like P of n equal to f of n plus g of n, where both are one discrete cases?
can you express, okay, you're saying now, what if you want to solve something where you've got multiple history? The answer is I don't think so, but I'd have to take a look at that. I mean, my initial reaction is that unless you understand why the theorem is holding, I'd be reluctant to try to get too ambitious with it. Okay, I'll try to give you some insight in a minute as to why it holds. Okay, but I wouldn't get too ambitious. The master theorem is a plug-and-chug kind of thing. Okay, at least if you want to understand it on the plug-and-chug level, that's good. Okay. Any questions about that? The third case is, again, now we've got t sub n is equal to 4n over 2 plus n cubed. Okay, we read it off. A, b, f sub n is now n cubed. We want to ask, is n cubed in big O of n to the 1.99? No, so case 1 doesn't apply. Is n cubed in big O of n squared? No. Okay, so case 2 doesn't apply. But is f of n, is n cubed, does it grow greater than n squared plus epsilon? The answer, is there a value? Yes, it does. So long as that epsilon is less than 1, n cubed is going to be less than 2 plus epsilon. So it's possible case 3 applies. We then have to go back down to the second clause. There's a second clause in the theorem which basically asks, is b times n to the, is basically b times n over a to the, plugging that thing in f of n, okay, is that less than this? Okay. That third clause is going to reduce to asking ourselves, is 4n over 2 raised to the 3 less than or equal to some constant times that? The answer is we plug in 1/2. N cubed is going to be, n over 2 cubed is n over 8. N over 8 times 4 is n over 2. Is there a value of c such that 1/2 n cubed is less than c times n cubed? So long as that constant is greater than 1/2, okay, this expression will be true, okay? And we needed a constant, again, the legality of the thing says if there's a constant such that that value is true and that constant is less than 1, then we have case 3 applies, okay? If so, then we can just plug it out. It turns out to be f of n, okay? The basic case of applying the master theorem, you compute this term, this log thing, okay? See how it compares to that, and then break it into cases based on that. Okay? Any questions about it? Okay? It's a plug-and-chug thing once you see it. You shouldn't be afraid of it. Okay? Now, why is the master theorem true? Okay, the master theorem, some of you will think, and if you want to think of it as this all-powerful black box, you can zone out for the next couple minutes. Okay? Okay, I see some people are going to take me up on that. Okay? If you don't want to see it and you want to see why the master theorem holds, the master theorem actually makes a lot of sense once you sit down and strip it out. Okay? Why is that? Suppose we've got a recurrence relation. T sub n equals a times t of n over b, t sub n over b plus f sub n. If we think about it, what we're really doing in the master theorem is the answer we give depends upon whether this function here, the additive stuff, is small, big, or just right. That's really the three cases of the master theorem. How much does the additive stuff contribute? Suppose that additive stuff contributed nothing. Suppose that additive term was the function f sub 0, f sub n equals 0. Meaning that the entire recurrence relation was simply going to be t of n times t sub n is equal to a times t of n over b. If the f of n is 0, there's no additive contribution. The only stuff making up the sum of our recurrence are those leaves. So let's look at our recurrence tree. The number of splitting that we do in the recursion tree, the degree of our split is going to be a. Okay? The amount of stuff that we have left, okay, is going to be basically is going to be n over b in each level. The degree of the split is going to be a. The amount of stuff that we have, okay, is getting divided by b each time. So the number of levels we have in this tree is going to be, we start out with n things. How many times do we divide it by b? before it gets down to being 1. That's the equivalent of saying that's the log base b of this thing. So we've got a splitter of a, that's the degree, raised to the height is how many leaves there's going to be. There's this many leaves. This is the value of what gets left behind. So what the master theorem is saying is, look, if, so long as f sub n is small enough, all the contribution, or most of the contribution, is from those leaves. And so all the master theorem is saying is count the leaves. Okay? Any questions about that case? Okay? When f sub n is small enough, count the leaves. Now, let's take the other case, which is case 3 of the recursion. Suppose f sub n is so big, okay, is bigger than our magic number. If we draw the recursion tree, let's look what's going to happen. Okay? If f sub n is big enough, at one point, the value of the stuff that we're adding is going to be bigger than the stuff of the leaves. Okay? That's clearly true. If we have a big enough function, all we're going to have to do is worry about this part. Okay? So how much stuff is there going to be in this entire tree? Well, if this function is really grows big enough, okay, f sub n is in fact going to be much bigger than all the terms on the second row. And if f sub n is in fact big enough, it's going to be large enough that it's going to be the total value of the tree is going to essentially be the value of just that one root call. Okay, if f sub n grows fast enough. Why is that? Well, let's take a look at an example. Suppose we had a case where f sub n was n cubed. Okay? And we were splitting it up into 3 calls. Okay? The 3 separate things, suppose we divided it, a was equal to 3. Okay, I mean, b was equal to 3. We divided it into 3 things, each of which was taking off n over 3 of it. N over 3 cubed is n over 27. If you had 3 of these things, okay, 3 times n over 27 is n over 9. Because n cubed grows so large relative to this n thing, okay, because these constants are such. The real sum of this thing is essentially just the root. Okay? And so case 3 of the master theorem is simply saying this grows so fast, all you really have to do is count that thing once. Okay? Case 2 of the master theorem says, well, you're in between them. Okay? And that's a little bit harder to technically show. But it makes sense that if you have one extreme and another extreme, somewhere in between there's going to be a middle. Okay? And that middle is case 2 of the master theorem. Okay? And this, I think, is understandable and gives you some idea as to why that's actually true, why the master theorem holds. Okay? Any questions about the master theorem? Okay? What I'd like to sort of finish with are 3 examples of famous algorithm problems, okay, by which the master theorem could tell you how fast the time actually is. Okay? What is the first problem? The first algorithm problem is something matrix multiplication. Okay? Everybody's multiplied matrices together. Okay? If you have an n by n matrix and you're multiplying it by an n by n matrix, how do you do it? Well, you've got n squared terms on the other side. Each term is the result of a dot product. You cruise down the row, you cruise down the column. You can multiply the value of this matrix can be represented as each element here can be the sum of n multiplications. So using that simple algorithm, that would take an n cubed time to do matrix multiplication. That's what you did in high school and all this kind of stuff. Amazingly, a guy named Strassen found a divide and conquer algorithm which computes matrix multiplication according to the following recurrence relation. To compute the product of 2n by n matrices, he could do it in 7 times Tn over 2 plus order n squared time. What did that mean? Well, n to the log of, well, that would really be saying we want to know what's the binary log of 7. That turns out to be 2.81. N to the 2.81 is greater than n squared. So it turns out case 1 of the master theorem works out. So Strasson's algorithm, in fact, shows that matrix multiplication can be done in n to the 2.81, which is better than n cubed, at least asymptotically. And in fact, by pulling these kind of shenanigans further, people have been able to get algorithms that run in n to the 2.38. Okay? And again, you're going to use the master theorem, just plug it in to get that. Famous algorithm, master theorem. Another famous problem, okay, is triangulation. This is a geometry problem. Suppose I give you a polygon, okay? You know, just sort of a, you know what a polygon is. It's just sort of a polygon. It's geometry, okay? When we do triangulating it, means that we're allowed to add internal edges, okay, to break it into smaller regions. I'm going to stop as soon as we get to the case where every region we define as a triangle. Okay, that's what we call triangulation. And it turns out triangulation is an important problem in graphics or just about any kind of a geometric application. One of the first things you want to do is to triangulate it. Okay? So how much time does it take to given a polygon? Again, each polygon can have more than one triangulation. So this guy looks a little differently than that guy. Don't worry about it. Okay? How hard is it to triangulate something? Well, in principle, one way an algorithm you could use would be to start with a polygon, find a pair of points that see each other without cutting through any edges you already had, add that edge, and now triangulate each part. Okay? And if you do that, again, it's a little tricky. I don't want to get into it. The big problem is trying to check to see whether or not you can add a diagonal without cutting anything else. Okay? This sort of trivial algorithm, if you sit down and analyze it, turns out to take something like n cubed. Okay, I won't defend the n cubed, but it should be clear that you go through all possible things, see if this line cuts it. If it does, find one that doesn't, and then just stick it in there. Okay, it's going to take something like n cubed. Using an amazingly clever and complicated algorithm, okay, Chazelle showed that you could do this using a divide and conquer algorithm where the time it takes would be t of n equals 2 tn over 2 plus order square root n time. Okay? Square root means n to the 1/2. N to the 1/2 is basically n to the 1 minus 1/2. So we could use case 1 of the master theorem. It turns out that by using this complicated algorithm, in fact, you could do it in linear time. Okay? So that's, again, a famous algorithm, nice, simple recursions.
Did you say n to the 1 minus 1/2?
N to the 1 minus 1/2. No, yeah, right. So here's what we got here. Square root of n is n to the 1/2. In order to see whether case 1 of the master theorem applies, you have to check to see is n to the 1/2 in big O of n to the 1 minus epsilon.
Okay. You just said 1 minus 1/2.
Okay.
I just got confused.
Okay, no problem. Okay, and so this is true for, so long as you can find a value of epsilon to do it, any value of epsilon greater than 0 and less than 1/2 will do the job. The final example the final example I'll show will be next class. We'll talk about sorting. Okay, and sorting can be solved using efficient algorithms which can be analyzed by that recurrence. Any questions? Okay, thanks for your attention. See you next time. Okay, bye.